Hey, good day. Hope you're doing well. And this week we're going to learn about how to predict what will happen to a reaction, a dynamic equilibrium actually, when it's perturbed, when it's messed with. So we're going to talk about our last big concept, and it's going to be involving chemical reactions and a new idea, chemical equilibrium. So we'll talk about that. We'll talk about how we show that with a reversible chemical reaction. Then we're going to learn about Le Chatelier's principle. And what that'll let us do is let us predict what will happen and discuss how amounts and temperatures and pressures affect. And that's the big thing that you're going to want to see. That's what our practice quiz. Before we get started, though, make sure you look at the practice that's available. You're going to be given an equilibrium. That's what this symbol means. You're going to be told what the change is. So if this goes up, and what you want to do is predict, hey, it's going to shift this way and make more of that, because you want to be able to understand how equilibrium works. So there's a lot of practice and there's an answer key for you. When you look at our work today, you really might want to review these online textbooks also, just because this concept can be challenging. But once you get the hang of it, once people get it, they really do well with it. So let's get started. Let's first of all remember that a chemical reaction is when chemical bonds break or form. You can form a bond between A and B. You can break that bond between A and C, or an old bond can break and a new bond can form. That's chemistry, right? And we like to think of that as a one-way reaction. But these processes, any intermolecular force or bond that can be made, can be broken. And so this could certainly break apart into that, or this could reform that. What we can see is that there is a equilibrium, between a dynamic equilibrium between these things being formed and these things being formed. And we show that with this symbol right here. This means that it's reversible. Almost every reaction really at some level is reversible. And A and B will form AB bonded, but AB bonded can break apart back into A and B. That's chemical equilibrium. And what we want to do is show you that we show that with reversible reactions. In a reversible reaction, the product, the original reactants, and the dynamic equilibrium, the rates of the forward and backward reactions are equal. So if we had this chemical reaction, and this would be highlighted, this is a reversible reaction symbolized by this symbol. Look for these two arrows. There's a lot of ways to represent that, but that's it. Imagine the forward reaction. Nitrogen and hydrogen forms ammonia. That's the forward reaction. That's the rate F. But then ammonia can break back down into nitrogen and hydrogen. That's the reverse reaction. Both of those reactions are happening at the same time. This is forming this, and this, you can see the arrow up there, is forming that. We can observe this and actually measure the rates, and what we find out is that there's amounts there. So you want to make sure you know what a reversible reaction is. Whenever you see this symbol, it's going forward and back, and we can start to think, oh, is there more of this side or more of that side? And that's what we'll look at as we go forward. It's a dynamic equilibrium. I love this guy. Look at him doing. And you think about what's going on an electrical system right there. If you're running on a treadmill, he really doesn't change position. He kind of stays in the same spot because he's moving one direction and the belt is moving the other direction. Those opposite directions have equal rates. The forward rate equals the reverse rate. So in essence, his positioning is right about here the whole time, even though he's moving dynamically this way and the belt's moving dynamically that way. That is what happens in equilibrium. These two opposing motions balance each other out. This is an equilibrium called a dynamic equilibrium. The dynamic simply means it's moving. It really just never stops. The forward reaction is always going on, and the reverse reaction is always going on. And that's what it means to be dynamic. You can also think about it as this. Imagine that there's person one and person two, and person one removes dirt at the same rate that two replaces it. One shovel goes up here, the other shovel goes up here, and the other shovel from two goes down here. The size of the hole and the piles of the dirt are going to remain the same. Imagine these two guys, here they are, and they move the dirt. And as long as they move the dirt at the same amount of time, as one puts a shovel full of dirt up here and two puts a shovel full of dirt up here, they'll start doing that continuously. That just never stops. That's a dynamic equilibrium. What we can observe, though, is that some things won't change. This pile of sand and this pile of dirt will stay the same. We could look at that ratio of the piles and we could put a number on it, and we do that in equilibrium that we talk about in AP chemistry. But the idea is it's dynamic, it just never stops. And these amounts then appear to be constant, but they aren't. Take a second and look at these two questions. What do you think the answer is? Chemical equilibrium is most often a dynamic process. What does that mean? Well, it simply means that the reactants continually turn into products and the products continually turn into reaction. It's a non-stop reaction. Good question two. Equilibrium is reached in a reversible chemical reactions. Well, how do we know it's at equilibrium? It doesn't start there, but it ends up there, and we know it's there when the concentration of reactants in the products does not change. They don't have to be equal. It doesn't have to mean 50% reactants, 50% products. It can be any sort of reaction. And remember, it's dynamic, so the reaction never stops. So what we want to do is talk about that equilibrium. And once it's established, we want to talk about how do we change it? What can we do to change the equilibrium? And this is a principle put forward by Le Chatelier. This is about a 150-year-old idea, and it simply says when a change is made to the conditions of a dynamic equilibrium, the system moves to counteract that change, causing changes in the quantities of reactants. So if you do something to stress an equilibrium, the equilibrium wants to undo that stress. So if I make it hotter, the equilibrium wants to make it do what it can to make it colder. And what we want to think about is this analogy, right? If I put a drop of water in here, that's a stress on this side. And so what happens? This water level will push this until I'm back to an equilibrium, right? Until I'm back to both levels. That's what equilibriums do. They always try to undo the stress. Most often we do it through concentration, temperature, and pressure changes. Let's start with talking about concentration. We're going to use this equilibrium the whole time. And what we want to do is think about what would happen if I had it at equilibrium and I added reactants, or I lowered the reactants. If I had it at equilibrium and I added more products or reduced the products, I can make a good prediction. Let's try this one with the reactants increase. The reactant concentrations increase. The equilibrium position shifts to reduce the reactant concentration. If I add more of this, it wants to undo that stress. It wants to remove some of that. The only way to remove that is to use this scoop here, and so it's going to shift this way and make more ammonia. This is a way to represent the shift, right? It is at equilibrium. Notice it looks like an equal sign, but once we do this stress, it's going to favor this side. There'll be a little bit more of this and a little bit less of that. What if I lower those? Well, the opposite, right? If I lower these to undo the stress, I want to replace what was taken away. So that means some of this ammonia has to form back into hydrogen and nitrogen to replace what's being lost. And we'll see the scoop arrow go the other way. Look at this. Let's talk about just the products. So this is all on the reactant side. On the product side, if I increase the amount of this when it's at equilibrium, well, to undo the stress, if there's too much of this, I wanted to have the reverse reaction go on, and you'll see that it shifts this way, and I'll make more nitrogen and hydrogen. And if I somehow can remove this, well, I want to replace that. I want to undo the stress and get it back. And so what you'll see is the scoopy arrow goes that way. This is the most basic way, and that's just by adding or removing actual reactants and products. That's what we can do to undo the stress. Hey, note this, catalysts do not affect equilibrium amounts. Catalyst, if I added a catalyst to this system, nothing would happen. The amounts wouldn't happen, it would just get there quicker. Catalyst just makes the rate go faster. It won't change the amount of reactants and products, like these stresses of concentration, temperature, or pressure. Let's look at temperature. If I know that this is an exothermic reaction, right? Heat is given off, exothermic, it's a product. If I increase the heat to undo that stress, I want to reduce the temperature, right? And to reduce the temperature, I want to use some of that heat that's added plus this and shift it this way, make more hydrogen and nitrogen. And so if I increase the heat, what we're going to do is move away from the heat. It's going to undo that stress. If I decrease the temperature, well, that means there's less heat being produced. And what do I want? I want to make some more heat to replace that. And so I would shift it this way, would shift towards more ammonia, and you would see this increase and this decrease. Catalysts, remember, they don't affect equilibrium amounts, just the amount of time to get to equilibrium. And finally, pressure. Importantly with pressure, what you have to do is look at the reactants and products, and you have to kind of mentally just sum up how many moles of gases are here. 1 mole of nitrogen, 3 moles of hydrogen, that's 4 moles of gas. How many moles of gas are here? 2 moles of gas. If those numbers are not equal, pressure will affect the equilibrium position. If those numbers are equal, pressure will have no effect on the equilibrium position. That's simply because this side with less moles of gas has actually got more order to it, a little less entropy. This side with 4 moles of gas actually has a lot more chaos in it. There's a lot more particles moving around. And pressure. Well, if you increase the pressure, and make it go up, the equilibrium will shift in a way to reduce the pressure. Well, 2 moles of gas make a certain amount of pressure. 4 moles of gas make more pressure. So if I increase the pressure, it's going to shift to the side that produces the least amount of pressure. 2 moles of gas, less particles colliding with the wall, means it's going to be the high pressure side is going to be the one with the lowest moles of gas. When we think about low pressure side, well, if you lower the pressure, let's make more pressure, right? Let's undo that and make more pressure. 4 moles of gas makes more pressure, and we would see it shift this way. Remember, catalysts don't affect the equilibrium amounts, just the amount of time it takes to get to equilibrium. So these are the 3 big ideas, and really I suggest you watch a few videos, do the practice, and check the answer key and get comfortable with it. Try these 2 questions out, take a second and think. Question 3, look at this chemical reaction. We want to shift to the right. This is the right side. We want it to become more reactant favored. What's going to do that? What will push it to the right? Well, if I add some NO, it would want to go this way. If I remove some NH3, if this goes away, it would want to replace what was being lost. If I decrease the temperature, let's see, it produces heat, and if I lower heat, it's going to want to make more heat. And so what we would see is that. Which one will cause it to shift to the right? We would say that it's decreasing temperature. Look at this reaction right here. Take a second to read this. Notice it's endothermic. This one we also want to shift to the right-hand side. Well, let's see. If the temperature goes up, it'll use that heat and make more of that. If the temperature goes down, it'll want to move this way to make more heat. For pressure, 2 moles of gas here, 2 moles of gas here, I bet you the correct answer right there is going to be A. So hopefully you kind of understand these questions and you can go through and think about this. This is a lab that we would have done. And this one is changing equilibrium and seeing colors. This equilibrium between iron nitrate and potassium thiocyanate produces this blood red iron thiocyanate ion. And so we would see this being yellow like irony water. I don't know if you've ever heard of seeing that. And of course, here's the blood colored iron thiocyanate. And notice these are all just concentration moves. If this goes up, you want to undo that stress. So if this goes up, it would want to shift this way and we would see it turn red. If we added more iron plus 3 ion, and this went up, again, we would see, well, to undo the stress, it wants to use it up and it would turn more red. If we had a chemical way of removing iron, like something that we could add that would remove iron, well, what we would see there is we would see the shift and we would see it turn yellow. So one of the things with Le Chatelier's is it's really often applied to how do we maximize products. A chemical engineer is going to want to know how can we make the most of, let's say, iron thiocyanate, this substance right here? And they would know that I need to continually pump in iron and potassium thiocyanate, and that would favor the production of this, and I would get more and more and more of it. But in an aqueous situation, pressure wouldn't matter, so everything's in a liquid. And we don't know if it's endothermic or exothermic. We'd have to do an experiment to figure that out. Remember, engineers want to maximize products. So you should be able to think through this. Like, here's an equilibrium, and in this equilibrium, we have methane and hydrogen sulfide, carbon disulfide and hydrogen. Notice on this side, 3 moles of gas, and on this side, 5 moles of gas. So pay attention to the amount of reactants and products. And if we wanted to shift them to the left, this side, what would we increase or decrease? If we wanted, as an engineer, to make more of this and shift it to the right, what are some things we could increase and decrease? Well, if you want it to shift this way, one of the things you do is add the pressure. Increase the pressure, right? Under high pressure, you would want to have 3 moles of reactants because they produce less pressure. So that would shift to remove particles, and these things would react, and we'd end up with more of that. If we want to shift to the left, we could also think about removing things, right? So if we remove the reactants, it'll shift, the products will shift and favor the reverse reaction to make more. If we wanted to make more of these things, let's say hydrogen for an alternative fuel, what we could do is increase the amount of reactants and products, reactants, just keep continually putting them in, or again, decrease the pressure. So it's possible you might want to think about, hey, what would be the situation that maximizes this? So do you have a good idea what a dynamic chemical equilibrium is? Remember, forward reactions and reverse reactions never stop. A reversible chemical reaction is that double arrow that we use, and it just shows us reactants and products separated as is. Le Chatelier's principle. And what it says is if you add a stress, the equilibrium will work to undo the stress. If you increase the temperature, you got to know if it's endothermic or exothermic. If you check out the pressures, it's got to have gases involved, and you got to see how many moles of gases are per turn. And of course, amounts. Amounts are the most common way. So you guys, make sure you do your practice this week and get in touch if you have any questions. This is your last big topic, and have a great week. Take care.